Hi Dinesh, am I audible? Hello Dinesh, can you confirm that I'm audible? Good evening. I'm audible, right? Okay, thanks for confirmation. Seems like you're the only one joined today's class. We will wait for a few minutes. Let's see if others are joining the class. So do you have Aspen with you now, Dinesh? Can we do a simulation? Okay, that's great. Then keep your Aspen ready, okay? We'll do a flow sheet simulation. Oh, this is your first session. No issues. You can unmute and talk. You need not have to put everything on chat. Just unmute and talk.
So good evening, sir.
Yeah, good evening, Dinesh. So you are doing all your assignments, right, till now?
Yes, sir.
Okay, fine. So no issues. If you have Aspen, we'll just we'll do a small flow sheet simulation today. Okay.
Okay, sir.
So just open it and keep it ready. It will take some time, right? So
Right, sir.
yeah, just open it, keep it ready.
Am I audible, sir?
Yeah, you're audible.
Okay, sir.
We'll just wait for a few more minutes, okay? Let's see if others are joining. Post that, we'll
Okay, sir.
continue with what I had planned for today's class, okay?
Okay, sir.
Okay. Hey Harshit, how are you? Hi Akshay, how was your week? Hi Arun, good evening. Oh, Arun's name is not in the list, but he sent a message. How? Interesting. Okay. So I'm hoping that people, whoever have joined the meeting, have Aspen now. Yes, right? Akshay, Arun, Harshit, Dinesh has. So no. Okay, thanks Harshit. Akshay and Arun, you two have, right? Okay, great. Okay, super. Then every one of the students who have joined have Aspen. So, if you remember, we simulated an air separation plant, right? In excuse me, in previous few weeks. Okay. So today we'll be you know, doing taking up one more flow sheet. Okay. So the basic idea is to do an optimization as well. However, based on the time, we may end up somewhere in between, or when we closing it. Okay. So yes, we'll get started. We are six, the regular batch. Fine. Okay. So in this week, professor basically was discussing about CO2 capture process. If you want to go into further details, you can just refer this book. Okay, it has got a lot of simulation things given all that. Okay, fine. So yeah, I have just only one question for you. Okay, so which of the following is used for regress absorption process modeling? Can you just put an answer on the chat box? So meanwhile, everyone, please open your Aspen and keep it ready. Okay, it will take some time, so you can cover it up later. It's great. Thanks for your responses. So when so everybody's on track when we are close to the end of the course. That's great. Good to see. So as you know, the separator models are used for something to design like a memory and separation or so and so. And the STWSM is based on assumptions. So it's based on Underwood assumption or many other assumptions as well. So it's a shortcut model for designing the distillation column, which will give us minimum required sorry trace and etc. Okay. Please excuse me. I have a throat infection, so in between, I may be stuffing. So please, I apologize for that. Maybe by next week I should be fine. So yes, the rat track is the model which through which we can properly design a distillation with hydraulic analysis, tray, packed, whatever we are interested in. So it can be used for isotropic distillation, reactive distillation, and absorption process as well. Okay, fine. So today, you all might be aware of LNG production, right? How it is produced. So basically, LNG, natural gas is taken from a core, and then it's liquefied. Okay, so it's liquefied using different liquefaction processes, in which one of the liquefaction process is shown over here. Okay, so we won't be simulating the entire process. However, just uh, the last section of the process we will be starting. Okay, so if you are interested, we can work on the full cycle simulation, provided we can finish in the time. Okay, in the next two classes whatever we have. So we'll just get started with the last heat exchanger to whatever see in this process. Okay, so this is what it says, right? So if you see, uh, a mixed refrigerant, a mixture of nitrogen and hydrocarbons, is used to liquefy the natural gas, which is at ambient temperature. Okay, so it's cooled down to temperatures less than 120 Kelvin and then expanded in a valve. Okay, then there is a phase separator which separates the gaseous part and the liquid part. So the liquid part is collected and called liquefied natural gas, which is LNG. Okay, in short. And then this refrigerant itself is cooled in a heat exchanger and expanded, and the expanded refrigerant is used to give the refrigeration required. Okay, so when you see any heat exchangers, you can see that it's in this example itself, you can see it's a two stream heat exchanger, right? You have one stream going in, which is getting cool, or which is getting hot, and which is getting heated. In another thing, there's another stream which is getting cooled, right? So normally you see only a two stream heat exchanger where it's possible that one is hot stream and another one is cold stream. However, in this example we can see that we have two hot streams, namely the stream which is going from 3 to 4, which is getting cooled down, and the stream which is getting 6 to 7, which is also getting cooled down. So in this process we have two hot streams and one cold stream. Okay, so we'll take up this example and try simulating this flow sheet. Okay, so So is all so now everyone ready with your Aspen, or shall we wait for some time? Similar to the last week exercise, we will try to do it parallelly. Okay. So I'll ask you to do one step. I'll wait for some time. I'll do that step. Okay. So everyone ready with the Aspen, right? Can't find. About where did you come across this compound, Mr. Maru? Why suddenly have this compound have come up? I just want to know. Is this related to any assignment question? Okay. So others, you had similar issue, or you are able to do it? Let me see. I don't know. 9 able to find it, right? See, I've just copy pasted whatever you have texted in the chat box, and I am able to get the compound. Can you please check it one more time? See, I'm able to find it, right? I didn't change anything. Whatever you have given, I just copy pasted. Probably you made some mistake. Okay? Please do check it. Okay, it's available. Okay, shall we continue with this? Okay, so if you want me to explain the process requirements, see, we want to cool this. Okay, however, the refrigerant is not sufficient enough to provide the cooling unless it is cooled and then expanded. Okay, so for that reason we cool it to temperatures of somewhere around 113 Kelvin. Okay, we cool it to near 113 Kelvin and then expand it from 24 bar to 4 bar, then get the refrigeration effect. Okay, this one compressor, it has got some isentropic efficiency. Okay, let's assume it to be 80%. uh, See, if you tell to a lecture 29, I don't remember what is that lecture 29. Can you just describe about what you're talking? See, whatever enthalpy change that we are getting in compression process is used for refrigeration. Okay, so it's just your first law of thermodynamics, right? So uh, it's taking heat from a low temperature body, which is Q, when the W work is given, and rejecting it to ambient. Okay, so this Q naught will be equal to W plus Q, whatever the refrigeration effect that's its recovery. Okay, how to add reactions in absorption column? So yeah, you can use your mic, no issues.
So since a cooling water, there is no hot vapor bypass in it, so the compressor discharge pressure will fluctuate. So the cooling duty won't be would be changing according to the pressure discharge pressure.
Okay,
So the
okay. Just
so the
let first give me the context about what you're talking. This particular question which I'm showing you.
yes,
Okay,
this
so
particular
in this
question.
question, what's your doubt?
So since you're telling that the duty is not sufficient enough, we are cooling the compressed gas, as in after the condenser, there is a the steam is being cooled by the after the valve, right?
Yes.
The steam 4 is being cooled by steam 5, right?
Stream 3 to 4 is being cooled by
By
stream 5 to 1. Correct.
5 to 1.
Correct.
Yes. So even if we don't put there inside the exchanger,
Hmm.
so what difference will it make? Because ultimately, whatever energy we are putting in it, we are extracting from the stream itself, right? As in, like, if I'm trying to understand it correctly.
I'll tell you. When you do an energy balance in this heat exchanger, what do you get? You get Q of 3 to 4 plus Q of 6 to 7 is equals to Q of 5 to 1. Am I right?
Yes, yes,
Right.
yes.
So the cold energy or the energy whichever the stream 5 to 1 is extracting is both from 3 to 4 as well as 6 to 7. Okay, so only a part of the cooling effect is being taken from the refrigerant and a part of it is taken from natural gas.
Okay, so if
All
you're
the
saying,
although it says condenser, consider it as an after cooler. Okay, it should be coined as an after cooler. It's not exactly condenser.
so you're telling me if I remove stream 3 to 4 from this exchanger,
Uh-huh.
it won't be as much effective
Yes.
as it is shown in this exchanger, right?
Yes. Correct. Because if you see the stream 3 temperature, it's 305 Kelvin. So when you expand the 305, refrigerant from 24 bar and 305 Kelvin, you will be able to see that the temperature to which it is expanded will be no more, no less than 200 Kelvin. We can try it out in fact in today's lecture itself. Okay. However, when you expand it from 113 Kelvin, you can go to the required temperatures. Okay. Since the required temperatures for LNG production are less than about 115 Kelvin, so you need to give refrigeration below that, right? Obviously, in practical world, we can't have heat transfer occurring at 0 delta T. That's not possible, right? So you need to go below that.
Okay, for that reason, because we require temperature 113 in the LNG, that is why
Yes,
we are cooling it.
yes.
Okay, fine. Thank you.
Okay, yeah, great. Can't find the exponent value. Can you tell how to find it? So you are asking about reactive distillation process. See, in lecture, I think professor has actually explained. See, in the reactions, first we need to create the reactions and then come back over here, right? That's what he has explained. See, you can use power
Yeah,
law. Yes, is who is this? Arun. Yeah, Arun.
yes, yeah, like that only. But see, when in that selection, I took reactive distillation, and when you enter the kinetic equation
Hmm.
and you enter all the details, after that, when you give the equation, you have to give the exponent also. Actually, that is not give explained in that video. Also, I downloaded the book. In that book, also, it is not given
Uh-huh.
what values you have to take. Yeah, this exponent value. You give the component, you can give the coefficient, but the what exponent you have to give, it is not given.
Uh,
Actually, I gave randomly and I tried cross checking, but my stream results are coming very different from what the professor has got in the lecture.
uh-huh. Okay. Is it
Is
not
it
in?
possible to buy it online? I also tried online. They are selling second order reaction, but I'm not able to get that.
No, is it not given in the video? Because I remember seeing it somewhere. I don't know where I see it. Okay, I'll come back to you, Arun, because I remember seeing this somewhere. Okay, I'll come back to you. Any other question do you have?
No, no, it is not.
Okay, I'll get back to you,
And
Arun.
also to that reaction, okay, in assignment question, another doubt is there. Maybe after this one, towards the end, we will discuss.
Okay, fine, fine. Okay. What is the another thing? Let me give myself. Eleven 87-3. Yeah. It's okay, we'll just get started with this, okay? Towards the end, I'll just answer your questions, okay? So, we have only 3 more lectures to go, so if you are interested in simulating flow sheet, we'll just get started. I'll come back to your questions in a minute, okay? Okay, fine. So, the first step, just open a fresh sheet and can you give all these components, whatever is being shown in this table? Nitrogen, methane, ethane, propane, N-butane, isobutane, pentane. Just take a screenshot of this, okay? Keep it with you. So let me also parallelly do this. This is nitrogen. See, I am able to get N-butane. Who had difficulty in getting N-butane? Dinesh, can you just check it one more time? See, all you need to do is just search N-butane here. You can search for isobutane also. See, it has come. When I says dibutane, it says isobutane. It's for ipentane. Right, so all of you are able to give the components, right? Okay, great. So use Peng Robinson, okay? PR equations. save this file. Okay, I'll keep this flow sheet no? Just I'll wait for some time. Okay, you just start with the compressor and the after cooler part. Okay, first put these two unit operations and tell me that you have completed, then I'll just complete. Peng Robinson, use Peng Robinson method. As of now, put only compressor and the after cooler, okay, the condenser. Sure. Just text me once you have completed giving these two. Then I'll also proceed. Okay. Which one you are not getting, Dinesh? You are not getting components. Did you get nitrogen, methane, ethane and propane? You didn't have any issue with these? So you have only issue with isobutane. I'll tell you, see, while searching for the components, okay, let me delete this. Let me delete these as well. I'll see when you click on find, type N hyphen butane. Okay, give hyphen in between. Don't write it continuously. Okay, just try it now. Do you still have the problem? And similarly for isobutane, I hyphen butane. Okay, great. Okay, so except Arun, others, have you completed the compressor and condenser part? Arun, you can carry on, you can go ahead. Okay, you need not have to wait. Just finish up the simulation. Use MHX. M heatx, not HX for cold box. No, the answer is only for Arun. Okay, others please continue with the compressor in the condenser part. So are you able to do compressor part, everyone? Akshay, Maru, Harshit, Dinesh. Okay, thanks for the response. Let me also do it. Okay, so all we need to do is pick up the compressor there, and then a cooler. Let me rename. Right, then a material stream taken as input. Let me use the same numbers. So this is 1, this is 2, and this is 3. Right, so 1 stream 1 details is 297 Kelvin, 4 bar, flow rate of 1. So 297 Kelvin, 4 bar, 1 mole per second, and given mole fraction, right? Given mole fraction 11.6 nitrogen, 28.4, 30.7, 14 propane, N-butane, 0 isobutane, right? So you can see that the stream 1 details are complete. Okay, now the compressor. So if you see, the compressor outlet 2 is going to 3, right? Since we are assuming the pressure drop to be 0, if you see in this process, so pressure of stream 3 is equal to pressure of stream 2. So stream 3, we can see that pressure is 24, so compressor outlet pressure will be 24. That's all we need to do with the compressor. Okay, then next go to condenser. Given the outlet of condenser is 3, it's 305 Kelvin, right? So let us write 305 Kelvin. Sorry, 305 Kelvin, and pressure drop is 0, right? That's all. Let's just run it. So you can see that results are available till here. Okay, fine. So till here everyone is able to find, it's coming 0.99, and that's fine, while tabulating we just round it off. Okay, so that's the reason it's coming 0.99, and that's okay, not a big difference. So now can everyone simulate the heat exchanger part? Heat exchanger and this V1 as well. Okay. Heat exchanger plus V1, simulate both of them. Use M heatx, okay, which is available here. M heatx, use this one. Just let me know if you are getting stuck somewhere, okay? Or once after you finish it up, just let me know. I'll proceed. The outlet pressure of compressor is 24 bar, okay? You can see here 24 bar. Assume pressure drop in the entire setup, pressure drop in heat exchangers and condensers is 0. So the pressure of compressor outlet is same as pressure at the state 3. So it's 24 bar, okay? So everyone is doing this, right? And I'm waiting for your responses. The heat exchanger and the valve part. Okay, thanks, Harshit. Others, what's your status? Okay. So for the people who have already completed the heat exchanger part also, now you can create a calculator block which calculates the efficiency of the process. Okay. Yes, you have two hot streams and one cold stream. You are correct, Arun. Heat exchanger has two hot streams and one cold stream.
For phase separator, we have to use flash too.
Yes, use flash too. What about others? Akshay, Maru, where are you? I'm assuming that you're solving this problem. forget it. So we have another stream, right? The natural gas stream. We'll take that. Okay. Now we have one heat exchanger. Pressure changes. We have two pressure changes, and then phase separator. Excuse me. So this 3 is hot stream to this. Right. Hot outlet, we have inlet to valve V1. And from V1 we have cold inlet to the heat exchanger. And from this we have the one which is coming out. We have another hot outlet, the valve. The valve outlet is connected to phase separator. One vapor and one liquid. Right. This is stream 6, one of the hot stream. Let me give the same label. This is 3, this is 4, this is 5, sorry, 5, this is 7, 8, 9, and 10. Right. Now let us give the required input. This can be called as 1A. So 6 is natural gas, which we are interested in, and which has got some input data required to be given. So 6 has a temperature of 300 Kelvin and 40 bar. 300 Kelvin, 40 bar, has a mole flow 0.4. Let us give mole fraction. So this nitrogen as 0.7, just 4%, 0.875, 57%, 0.5. That's all. That's the input data which we need to give for this stream. And let's click on next. It's taking us to heat exchanger. Okay. So if you observe in the system, there's a possibility that the CP is just varying quite significantly in this system, right? Because the temperature change is very high. So in this case, there's an always possibility of internal pinch. So what do we do in that case? We'll just click the zonal analysis. We'll say we'll give some zones to be 20, and we'll ask to add additional zones if required. Okay. So this makes sure that the internal pinch in the heat exchangers are considered. So temperature 4 is 113 and temperature 7 is also 113. Let me change it to Kelvin. Right. So done with heat exchanger, and then we have phase separator. We'll say pressure drop is 0 and heat QP is 0. Right. Next we have V1. So V1 has got outlet pressure of 4 bar. Right? So 4 bar. And V2 has pressure of 1 bar. Okay, describe it here. So that's all. So once after giving all the required input, it says the required input is complete. Right? Just run this. You can see that the simulation is ready and we have results, right? Let us just see the heat exchanger. So everyone, you are able to simulate the flow sheet, right? Can you please respond if you are unable to simulate the flow sheet? Every one of you are able to simulate it? No, it's an additional given information which is not here, okay? I didn't tell you prior. So it's expanded to 1 bar, okay? Natural gas after cooling is expanded to 1 bar. Except that anything else? So everyone able to simulate this flow sheet? Okay, got confirmation from one. Others? Flash tank pressure is 1 bar. No, see, the input which you give over here, if you give 0, it will consider the pressure drop to be 0, okay? So any value greater than 1, it will say the outlet pressure value. So you can either give 0 or 1. It doesn't matter in this case because anyways we are expanding it to 1 bar. However, it is a wise thing to give a pressure drop to be 0 because if we are doing an optimization thing, then we'll keep this one as a variable, okay? So in that case, if we give pressure drop to be 0, then it will add, we'll have some more advantage in optimization, okay? Others, you are able to simulate the flow sheet? Okay, need 5 minutes. Okay, please continue. I'll wait for some time. Others just take a screenshot of the question, okay? So in case if you are unable to finish it today, just finish it as an home assignment and it will be a practice for you. Anyways, I'll be sharing the slides online, okay? So you can get there as well. So, sorry, I didn't realize that was muted. I was talking here. Okay, fine. So everyone, you are able to finish it, right? specifications for heat exchanger. Okay, see, all you need to give is you need to define which input stream corresponds to which output stream. Okay, for example, 3 corresponds to 4, 5 corresponds to 1A, and 6 corresponds to 7. Okay, and we need to specify the temperature value. And one more thing which we specified is the zonal analysis. We said the number of internal zones that we need at least is 20, and we have asked to add some more zones if the profile is found to be non-linear. Okay, non-linear is with respect to CP. If CP is varying non-linearly with temperature, then consider some more zonal. Okay, that's the input for heat exchanger. That's all. See, I'll be sharing these slides online, okay? You can download it and try finish it if you are unable to finish in this class. Shall we do an optimization in the same process in the next class, or shall I get a new flow sheet? What do you say? We can add an optimizer to this to maximize the efficiency. So it will be a practice for you on usage of optimization tool. Or if you want to simulate another flow sheet, I can get a new flow sheet as well. Which one would you prefer? Shall we do an optimization or some new flow sheet in the coming week? So you are sure that in half the lecture we'll be able to finish optimization? Okay, then we'll try this out then. So I actually prepared for today's class itself the optimization. Okay, so maybe we'll do after class the optimization and then a new flow sheet. We'll see to what extent we'll be able to do. If everyone is getting results in this project, then we can continue with this. Okay, let's see if everybody is able to get. So do it in your home and see if you are able to get the same result. So also we need to add a calculator block. Okay, so maybe we'll get started with the adding calculator block in the next class. Then we'll see the optimization and new flow sheet as well. Okay, yes, correct, I remember your question. See, it's actually clearly shown in the lecture. I don't know if you have missed. So all you need to do is when you have a column, okay. See, first you need to specify a reaction over here. Okay, give some ID. Is it based on free radical, general, ionic, or power law? Normally, most of the examples which we are dealing with are based on power law. Okay, just specify some reaction given the components. Okay, if you're talking of water gas shift reaction or uh, let's say ammonia production, whatever is the example, just give the reaction over here. Once you have the reaction ID, okay, once you have the kinetics where you have all the activation energy, T, etc., K, okay, everything, then go to the column under specifications. It will ask you reaction. Okay, so you need to specify reaction ID over here. Okay, that's all you need to do. So you need to specify from which stage to which stage the reaction is happening and the reaction ID which you have already created previously under the reactions tab. Okay, that's all you need to do. So what do we need to optimize? So see, we have calculated some efficiency, right? We need to maximize the efficiency and find the refrigerant composition. Okay, so we need to find the refrigerant composition which maximizes this efficiency. That's our aim in this question. 3 to 4 is called adiabatic flashing, so it reduces vapor. Example, can 3 to 4 be called adiabatic flashing? What is this 3 to 4? No, it's not adiabatic. No, it's not. It's nowhere related to compressor work. No. His exponent is, what is OT? Okay, not okay. There's an N missing. Exponent is not mentioned. Then is there a way to find in reactions? Uh, okay. So you are talking of the previous thing. Okay, I got it. The exponent, which this one, right? No, I don't know if there is a way to find. I don't know. I can't answer this question at this point. Please give reference for biogas production simulation. I'll have to look back, okay? Maybe I'll text you guys in a mail for the reference. It is. See, I have order of reaction. See, with half knowledge, I shouldn't answer. Okay, so better I come back with the proper answer. In first glance, I had an idea that it's the order of reaction, but then without having a confirmation, I shouldn't share around. Okay, so that's why I kept quiet. I'll get back to you. Any other question? The set rate track column is at 30 bar. Set. I'm just reading the above question.